Friends, welcome to the 18th lecture on module 2. So, this is going to be lecture 18 on module 2, where I am continuing with the discussion on application problem. Which I am continuing. So, just to recollect, we are looking forward for the safety assessment of a triangular configuration tensional platform where the predominant wave direction is along the surge axis. It is subjected to distinctly high C waves which we know how to generate them using the modification suggested by Mitchell 1999, and we have got a modified PM spectrum based on which you can generate the forces arising from the hydrodynamic effects caused by the distinctly high C waves, because you have to qualify actually a wave as a distinctly high C wave by comparing the wave elevation with the preceding and successive wave history. We have already shown a window in the last lecture how the wave elevation is seen as a concave front and convex rear, which qualifies for a wave to be called as a distinctly high C waves. The second force acting is the seismic excitation. In this study, seismic excitation is considered as horizontal and vertical, along surge and along heave. Of course, along sway it is neglected, okay, along x, that is displacement x1 g and displacement x3 g are considered in the study, okay. And we already said this will cause a dynamic tether tension variation which can be given by the equation specified. Now, it actually requires a random time history for the ground motion, okay. The ground motion need to be also simulated, because earthquakes which are occurring at the seabed are not actually measured. Therefore, one need to actually simulate this kind of a seismic signal which will closely related to the sea quake or earthquake caused in one of the TLPs or the region of TLP where it is located. I will come to that slightly later. So, I need to have a spectrum. So, I am going to use the famous Kanai-Tazimi power spectrum to simulate the seismic signal. The one sided power spectral density function is given by So, the one sided power spectral density function to simulate the seismic signal using Kanai-Tazimi power spectral density function is given by the equation 1, which is multiplied by S naught, where S naught is given by So, in this case omega g and zeta g are natural frequency and damping ratio of the ground motion. So, to determine this, it depends on many factors. One is the local earth surface layer. That is one character, which need to be actually simulated according to the real time simulation happened or real earthquake happened in one of the regions where TLP is located. Sigma g square, which is a variable here, okay, which is a variable here, is actually the variance of the ground acceleration. S0 is actually the intensity of the earthquake. Okay. We should say intensity of excitation. So, there are three parameters here. So, the three parameters of the KT spectrum, that is Kanai-Tazimi power spectrum, are essentially omega g, that is the frequency of ground excitation, the damping of the ground excitation, and of course, the intensity S naught. Okay. Now, to simulate this, you need to estimate this. So, they need to be estimated from the what we call representative earthquake records, using statistical estimation process. Okay, we need to use this. So, now we have in this study selected an artificial earthquake is simulated in the present study to match the peak velocity of the earthquake occurred in Gulf of Mexico. Okay. So, the occurrence was Richter scale 5.8 magnitude, the location is miles west of Anna Maria, Florida. Which occurred on 10/9/2006 at 14:56:07. This is coordinated universal time. Epicenter was on 26.34 north, 86.57 west, that is epicenter. So, there is an earthquake which occurred in one of the locations where the platform is situated, Okay. Interestingly, there is a Mars TLP which is located or operating in Mississippi Canyon block, which is also located in Gulf of Mexico. Okay. So, the example was just to study what would be the safety issue related to this TLP when this TLP is subjected to, or a similar TLP of this order is subjected to a combination of hydrodynamic loads arising from distinctly high sea quakes, distinctly high sea waves and earthquake signals. One can ask me a question, how this is practical, that a TLP already existing and locating will be subjected to such distinctly higher order combination. That is about reliability. Reliability is actually considering the performance of a function or a system for its intended performance of a function for a given period of time for a worst combination. We are looking for the safety of the system. If this combination occurs where there is a possibility that an earthquake occurred in this location of this epicenter. So, in this study a distinctly high sea waves were created using modified PM spectrum and a earthquake signal was generated, simulated using Kanai-Tazimi spectrum, which will now match, which I will show you, which will match with that of the measured signal intensity, and of course, the location is as close to the epicenter of this particular TLP. Okay. The actual earthquake had a peak ground acceleration as 0.25 g and velocity as 0.29 meter per second. The artificial earthquake generated using Kanai-Tazimi spectrum had ground acceleration which is 0.25 to 0.39 g and velocity 0.2 to 0.3 meter per second, which is close to what we have here. Okay. The frequency of motion which is required for the simulation is set as 2.5 hertz for the firm ground. As suggested by Nigam 1983. The other parameters in KT spectrum are chosen accordingly, so that the ground acceleration and the velocity which is simulated is or match with the measured value. So, it is a trial and error process by which we can select the parameters such that the simulated velocity and acceleration matches closely with that of the actual earthquake. So, please pay attention to the figure shown on the screen now. The screen on the left side shows the power spectral density function of the vertical ground acceleration, on the right side it shows the time history of the ground velocity. This has been simulated now using Kanai-Tazimi power spectrum with 3 parameter variation, one side spectral density is given in the equation in the blackboard. So, the parameter is chosen in such a manner that the simulated earthquake refers essentially or represents ideally the actual earthquake occurred in an epicenter as shown in the blackboard here. Now, as we understand, when the simulated earthquake is imposed, on the TLP for numerical study. We now agree that it will cause delta T, okay, delta T, that is teether tension variation. Therefore, the stiffness coefficients will be updated at every time instant which will now make the equation of motion completely dependent on two issues. One is the variation in the stiffness coefficient, other is variable submergence created due to the aerodynamic loading. Okay. So, now as we said, the force vector comprises of two things. One is due to aerodynamic loading, caused by distinctly high sea waves. The second is variation in teether tension caused by earthquake imposed on the seabed, both horizontal and vertical. Now, we need to apply this particular loading on the TLP. So, we picked up 3 TLPs. Now, the study is focusing on triangular TLP is the focus, whereas Mars TLP located in Mississippi Canyon block is not a triangular TLP, it is having 4 legs. Okay. So, the study is essentially focusing on the safety or reliability or the performance of intended function of the system under the worst combination of loads for a specific case study where real earthquake has actually occurred in the same location and intensity, of course, ground velocity and acceleration are found to be matching from the simulated with that of the real one. So, kindly pay attention to the example TLP properties shown on the screen. So, there are 3 TLPs taken for the study, TLP 1, 2 and 3. The weight, the buoyancy, initial teether tension, teether length and water depths are actually considered and shown in the figure in the tabular form. Now, all these are essentially meant for a square platform, okay. All these are essentially meant for a square platform. So, the square platform will have 4 legs. We need to simulate a triangular geometry which can sustain and found to be safe with that of the worst combination of hydrodynamic loading and the seismic forces caused by the Kanight-Azimi power spectrum. So, to simulate this, the geometric properties of 3 square TLPs at different water depths are compared. So, 3 TLPs taken from the literature. Are compared, 2002A are compared to arrive at an equivalent triangular geometry. Okay. To arrive at that, there are 2 conditions to be maintained. One is, let us say the buoyancy force is essentially given by 4 T naught plus W for square TLP, whereas this is equal to 3 T naught plus W for a triangular TLP. Let us say this triangular TLP, calling this equation number let us say 2. So, one can see that T0 in the triangular TLP is kept same as that of square TLP. So, since the total tension in triangular TLP is lesser than that of square TLP, weight is increased. Okay. So, now the second variation is going to be the inertia coefficient of inertia Cm. This is interpolated using a second degree polynomial. So, Cm of y is taken as P1 y square plus P2 y plus P3, and for different TLPs the Cm values which are taken are shown in the screen now. Please look at the screen, you will know the different coefficients P1, P2 and P3 which are used to calculate Cm as a function of depth, which are used for different TLPs are given here. Okay. So, the hydrodynamic inertia coefficient is also varied along the depth as a second order or second degree polynomial as shown in the equation here. In this case, y is measured from the seabed. So, free vibration analysis are conducted to actually calculate the natural periods of TLP. So, pay attention to the table shown in the screen now. For different TLP nomenclature, that is TLP1, TLP2 and TLP3, whose geometric properties are shown earlier, the natural frequencies and periods in different degrees of freedom which are active for this present study are shown in the table. So, one can pay attention to the surge periods which makes the TLP highly flexible, one can pay attention to the heave and pitch periods which actually makes a TLP stiff in these 2 degrees of freedom. Therefore, TLP, as we all agree and understand, is an hybrid system. On horizontal plane it is flexible, and on the vertical plane it is very rigid. Okay. So, the periods obtained using free vibration analysis are shown in the table here. So, interestingly, if you look at the values for the heave period of all the TLPs, if you look at the values, the heave frequency is closer to that of the high sea waves or distinctly high. Sea waves, because we know the modal frequency used in the PM spectrum is 0.46 hertz, okay, used in the study. If you pay attention to the values shown in the screen now, the heave periods are considered to be closer in terms of the frequency, closer to the modal frequency which is used for simulating the hydrodynamic loads as distinctly high sea waves. Now, equation of motion becomes iterative now, the solution becomes iterative. Solution of equation of motion of TLP under the combination of hydrodynamic and earthquake loads becomes iterative. So, Newmark's integration scheme is used solve the equation of motion which is iterative in nature. Why? Because of two reasons. One is it is dependent on structural response. 2, the stiffness coefficients are updated due to dynamic tether tension variation. Third, because of set down effects which is variable submergence. Therefore, the Newmark's beta integration scheme has a specific value. In the study, alpha is taken as 0.25 and delta is taken as 0.5 for this scheme. Okay. The reference could be Bathe and Wilson, 1987. So, various non-linearities are present in the system. One, it can arise from change in stiffness coefficients. Which is caused because of delta T, which is essentially caused due to earthquake excitation. The second could be the added mass term, which is due to variable submergence effect. The third could be the set down effect. The fourth could be evaluation of hydrodynamic forces. At instantaneous displaced position of TL, that is response dependence. Okay. The non-linearities arise from these following cases. So, one can easily understand here that the dynamic tether tension variation caused by the seismic excitation is an important factor influencing the response of TLP. That too, in the presence of distinctly high sea waves, the event can be considered as a critical combination which becomes the input load for the reliability analysis. So, one can see here the change in tension in tethers causes indirect load on TLP. It is not direct because TLP does not rest on the seabed. Please pay attention to the response summary of the triangular TLPs after the equations of motions are solved in the Newmark's integration scheme as discussed just now. So, please pay attention to the values shown on the screen now. 3 TLPs, TLP 1, 2 and 3 are listed here. Both time history response are given for heave, pitch and surge degrees of freedom. So, one can see here that the power spectral density peaks in heave occurs at different frequencies, for pitch at different frequencies and surge at different frequencies as seen here for all the 3 TLPs. There is an interesting commonness between the peaks occurred in all the degrees of freedom. This peak of 1.588 is seen in almost all degrees of freedom, is almost seen in all TLPs. Please understand, these TLPs are actually simulated TLPs having similar characteristics as that of a 4-legged TLP, of course with 3 legs interpreting lesser T0 and greater weight. We are looking for a stability of the geometric configuration of triangular compared to that of square under the worst combination of forces. That is the example problem what we are looking at now. So, one can see here that the peak occurring at 1.588 hertz is seen in almost all degrees of freedom in the response in all TLPs, and one can also see the dynamic tether tension variation caused by the seismic excitation forces imposed on the tether connectivity causes change in tether tension as high as 65.43% compared to the initial pretension, and 20% is the minimum value. It also imposes strain in the tethers varying about 0.298% and as low as 0.109% strain in the tethers. Kindly pay attention to the response time history under the seismic forces and distinctly high sea waves. There are 3 sets of figures here. First set shows for TLP 1, second set for TLP 2, third set for TLP 3. For our understanding, TLP 1, 2 and 3 are located at different water depths as shown in the previous table earlier. So, one can see here the heave response, the pitch and surge response of TLPs 1, 2 and 3 respectively on the screen as shown, which is now under the combination of seismic forces caused by Kanai-Tajimi spectrum simulated and with that of the distinctly high sea wave simulated using modified Pearson-Musgrave spectrum. The whole problem is solved in a iterative scheme using Newmark's beta technique as explained just now. So, looking at this variation, one can see the following: the percentage change in tether tension is computed as follows. For example, let us say in case of TLP 1, if the maximum heave response is 1.203 meters and the surge response at this time instance is 0.7212 meters. Okay. let us say the heave response for this theta. The heave response is known, the surge response also known at the specific time. So, change in length delta L is actually taken as sum of square root of the squares, which is 1.203 square plus 0.7212 square, that gives me the change in length, which is in this case 1.4029. Once you know this, the additional dynamic theta tension variation can be simply AE by L of that particular value multiplied by this delta L. So, for example, in this case it is going to be 58060 multiplied by 1.4029. So, the additional tension variation is going to be 81455.95 kilonewton. So, that is how it has been calculated. Therefore, percentage change in theta tension is simply the additional dynamic theta tension divided by initial T naught. So, that is going to be 81455.995, let us say, divided by 124,500, that is the initial T naught, which is amounting to 65.43%. Okay. That is what we have shown in the table as the percentage theta tension variation. Okay. Similarly, for TLP2, this value is 41.61%, and for TLP3 this value is calculated as 20.31%. Now, one is also worried whether the tethers have yielded or not. So, to check whether tethers have yielded under this change in tension, we have also plotted the strain in tethers. Or computed, and table shows the values of strain also, as you can see from the table. Okay. So, one can easily infer the following: the dynamic theta tension variation is reduced considerably with increase in water depth, because you know TLP 1, 2 and 3 are for different water depths. But interestingly, this variation is neither proportional to change in water depth nor initial T0. So, the results can be superimposed in terms of power spectral density plots. Please pay attention to the power spectral density plots shown on the screen now for different TLPs 1, 2 and 3. One can easily see in all the cases in heave response, let us say in TLP 1, there are two peaks occurring, one is about 1.588, one is of course around 0.675. Of course, at 1.588 in all the cases you can see the peak is occurring, okay, in all the cases TLP 1, TLP 2 and TLP 3, whose summary is also shown in the table. The power spectral density functions are the curves, the PSD plots which has been shown for different TLP, shown that at a frequency of 0.5 hertz, approximately 0.5 hertz, one can see a peak. In general, it can be seen that all degrees of freedom show high frequency response. Okay? All degrees of freedom show high frequency response. And there is no visible damping effects because the response dies down with time. Frequency responses are narrow banded with energy concentration as follows. 1. The heave response is shown at 3 distinct peaks. One is at 0 frequency, close to 0 frequency, which is very small, therefore can be neglected. The other is at mid frequency, which is very close to the natural frequency of, let us say, TLP1 and TLP2 at least, and it is double of the frequency of the natural frequency for TLP3. There is a peak which is occurring at 1.588 hertz, which is very near very close to the average peaks of Kanitazmi spectrum and Pearson Moskowitz spectrum. If you look at the pitch response, again it shows 3 distinct peaks. One occurring, the first one close to near 0, which is 0.04 hertz for TLP1 and TLP2, 0.02 for TLP3. The second one occurs close to natural frequency, for at least TLP1 and TLP2 and twice the natural frequency for TLP3. The third little peak occurs at 1.588 hertz with average of PM and KT spectrum. So, it is very interesting, the peak occurring at 1.588, which would have been missing when this combination not studied, is a clear manifestation of earthquake forces combined with distinctly high sea waves. This is influencing all active degrees of freedom. What do you mean by active degrees of freedom? The platform actually has only unidirectional wave acting. So, only certain degrees of freedom are active. One is surge, other is heave, another is pitch. The remaining degrees of freedom like sway, roll and yaw will be absent because of symmetry or because of wave not present in the direction predominantly. So, only active degrees of freedom which are present in the system are influenced by the critical combination of the earthquake forces and the distinctly sea waves which is brought out in the specific study. So, interestingly, if you look at the phase plots shown on the screen now, friends, the phase plots are shown for a combination of distinctly sea waves and seismic forces imposed for all 3 TLPs, TLP1, TLP2 and TLP3. So, looking at the phase plots, one can say, and looking at the PSD values, one can say it is narrow banded and TLP is lesser excited because of greater water depth. The system is negligible for higher frequency responses. Phase plots being elliptical in nature affirm that all states are stable and periodic. So, for a given combination of distinctly sea waves and earthquake forces generated, one can check the stability and safety of a given system under the worst combination, and the phase plot shown as a typical response of the TLP for this particular combination of forces shows they are elliptical in nature, which confirms that all states are stable and periodic. Of course, the period is longer because the major axis of the ellipse is longer. So, from the example study, one can easily understand that dynamic tether tension variation can be checked under excessive or exceptional combinations to check whether this combination would cause challenge the safety of the given system. Clearly, the peak seen in the response in all 3 active degrees of freedom, namely heave, pitch and surge, occurring at the average sum frequencies of PM spectrum and KG spectrum is a clear manifestation of this combination. While TLPs are expected to be rigid in stiff degree of freedom, in this specific case one can see that heave is activated even at 1.58 hertz frequency, which is very dangerous for a given system, because heave is supposed to be the stiff degree of freedom. So, displacement in heave degree caused by the seismic excitation in combination with distinctly sea waves is actually an interesting challenge study, which tells me whether the platform geometry is stable and safe under this given combination. So, reliability study can be also examined indirectly by checking the stability or safety of the platform, as we saw in 2 example studies. The first case was Matthew stability in example 1. The second case is the worst combination where we are checking for the safety of the system using phase plots. I hope these 2 application problems are interesting and you have understood the application of reliability with these problems. Thank you very much.